Paris. We're going to get started now. So Astronomy on Tap is an international organization for science outreach, and there are over 100 locations around the world. And so we just started this location in Paris. This is our second event, and we're really happy to bring you two great speakers today. So the format will be, there will be two talks, 20-minute talks, time for questions afterwards, and then there will be a 15 to 20-minute break between the talks, and that's how tonight's going to run. So I will introduce our first speaker, Dr. Miguel Montargès. He is a postdoctoral researcher at the Observatoire de Paris, at the Laboratoire d'études spatiales et d'instrumentation en Astrophysique. He is interested in the study of cool evolved stars, red giants and supergiants, and how they seed the interstellar medium to form new stars and potentially planets and life. He uses state-of-the-art facilities such as the Very Large Telescope and the Atacama Large Millimeter Array, both in Chile, and numerical simulations to do his work. So thank you, Dr. Montargès. We'll get the slides up.
Thank you. I'm always stressed when people applause before because I don't know how the presentation will go. I need that too.
Yeah, if you can just plug it on.
This. Fine. So I'm going to talk to this evening about my favorite subject, which is the red supergiant star Betelgeuse. Normally, if the weather had been with us, we could have seen it in the sky at the end of the presentation, but we are in Paris. So there will be a special event in December 12, and that will be the second part of the presentation. But first, I would like to tell you what star is Betelgeuse and how you can recognize it. So this is the Orion constellation, where you have what you can see in winter, and it's super easy to find, even in central Paris, because you have these three stars that are aligned. So you can see it on the southeast at 11 currently in the evening. It will be earlier as the winter comes. So here the three central stars that are the Orion belts. Here you have a blue giant, and here on the top left you have a red star that is Betelgeuse, and you can really see the color with the eye. So you can see it is orange, and it's one of the rare stars on which you can see the color with the naked eye. So the star itself is quite impressive, so I want to present it to you, and for that I need a comparison, because if I just give numbers in kilometers, distance, kilograms, it will not mean anything. So I'm comparing here the star, Betelgeuse, to a famous star that you all know about, the Sun, our star. So first the distance. The Sun is 8 light minutes from here. So now if I shut down the Sun just like that, it will take 8 minutes for us to not see it because it's already the night. But if we were in the date, you get the idea. Betelgeuse, it's 724 light years away. So of course, if I shut down Betelgeuse now, it will take more than 700 years for us to see it. So it's very far. The size of the star. So the size of the Sun, it's relatively easy. It's 1 solar radius because it's the definition. Another way to say that is 110 Earth radius. This means that on the equator of the Sun, you can put 100 Earth. On the equator of Betelgeuse, you can put 900 suns. And on each sun you can put, of course, 100 Earth. So this is really a big star. And the way people say that is, oh, this is a star that is 1,000 times bigger than the Sun. This is not the case, because when you talk about bigger, you mean the volume. And if you talk about the volume, you need to use the cube of that. And in the volume of Betelgeuse, you can put 1 billion suns. So this is really a big star. And yet, inside this star, you have only 15 to 20 solar masses. So this is something very big, but not very heavy in comparison to its size. And basically the density, particularly of the external envelope, is much lower than the density of the Sun. The temperature is about 3,400 K, meaning that this is a cool star. Of course, for us it's warm, but compared to the temperature of the Sun, 500 K, it's cool. And it is super bright, so the luminosity, it says that it's 10,000 times more luminous than the Sun, which is totally useless for us tonight, but it's a way to say that it is very bright and to be proud of the star I prefer. And it has no non-companion, so all massive stars, normally they are not alone, there are two stars orbiting each other, and this one, it's alone, and we wonder why. So it's a red supergiant, but it has not always been a red supergiant. Stars, they evolve with time, so they are born in nebulae, so stellar nurseries. If they are lower than 8 solar mass, they live a life like the Sun of about 10 billion years, so they become a yellow dwarf. The Sun is a yellow dwarf. Then red giant, then they expel the external layer to form a planetary nebula with a white dwarf at the center, and after a few thousand years only the white dwarf remains, and part of the material comes back toward the interstellar medium. Massive stars above 8 solar mass, they become blue giants, so hot and warm, red supergiant as I said, and they explode. Here is just a wind that is removing the external layer. This one and Betelgeuse are going to explode as supernovae, and when that happens they are as bright as 100 billion stars, so they become as bright as an entire galaxy. When it happens in our galaxy, a star becomes as bright as the full moon. Last time it happened was 400 years, so we'll see when will be the next time. And after, only a neutron star or a black hole remain, and part of the material goes back toward the interstellar medium. Normally, Betelgeuse should become a neutron star, but there are some chances that it could be a black hole. So this was the simple view that we are taught in high school normally, and the more complex view when we are astronomers is that, so there are plenty of ways for stars to evolve. So here you have time and the initial mass, and you see I presented only those two ones, but actually what we do in astrophysics is much more complex, and the way it's going to evolve depends on the rotation rate of the star, if it has a companion, and the way it loses material. So it's much more complex than the simplest view that we are taught normally. So this is an artist's impression of Betelgeuse that was done about 10 years ago, but is still accurate. So here you have the star that does not look like the Sun at all, and here you have the solar system at the same scale. And what I like to say, and what people ask me, is how Betelgeuse would look like if it were in the solar system. Well, for us it would look like nothing, because we would be inside the star. So the limit of the star is at the orbit of Jupiter. This is Jupiter, Saturn, Uranus, Neptune, and here the four small dots are us: Mercury, Venus, Earth, and Mars. So this is again something very, very huge. And you have these cells, convective cells, on the surface of the star that are basically like when you try to cook pasta. Well, succeed to cook pasta in your own kitchen, where you have the pasta. So small ones, you need coquillettes are preferable because spaghettis are too long and they are not going to move. So coquillettes are better, and they are at the bottom of the beginning of the water. Then it's heating, so it's coming up because of convection, cooling at the surface of the air of your kitchen, and sinking down. And what we see here, and you can launch the movie please, is exactly the same stuff without pasta, but come back and you have to click on the image. So if you have the pointer, yeah, yes, click. This is a simulation of what a red supergiant looks like. And basically you have the hot material coming from the depths, that is bright, that is warm, that is cooling at the surface with the contact of the interplanetary medium, cooling so it's black, and then it sinks down towards the depths of the star. And on the Sun you have also this structure, convection, but you have 1 million convective cells that are about the size of France, so 1,000 kilometers. Here you have a few convective cells, like 10, 20, that are about the size of the star, not the sun, the size of this star. So this is completely different physics compared to what we have on the sun. I'm going to, you can close the... you can do, wait. No problem. So, and a question we are wondering is, well, we see that there is a star, and we see that it's surrounded by material. It's what we call the mass loss, the wind of the star, like there is a solar wind. There are stellar winds with material outflowing from the star, and this is stardust. So this is what we call stardust, dust made from stars, from material expelled from the stars. If there are French people in the room, you know that Hubert Reeves died almost exactly 1 month ago, and he was the one who taught people that we are made of stardust. And basically this is made inside this kind of star, and you have the dust that is living with the gas, the star, and we do not know how it is leaving the surface of the star. So we see that there is material coming from the star. We see a star with motions on its surface, but we do not know how the material lives. We don't have the physical ingredient for that. And that's what I'm trying to do with observations and simulation to understand how the material is leaving the surface of the star. And well, we have several possibilities. So first we wonder how dust forms, because it's not clear, the chemical pathway, how to launch the material, and several possibilities. So something linked to the convective motions I've shown, perhaps something linked to magnetic field. Well, basically when we do not know something in astrophysics, we always say it is either magnetic field or another star hidden somewhere. So we always put magnetic field somewhere. And of course the velocity in the convective pattern. And because you have all this motion on the surface, all red supergiants, they are variable stars. So this is the light curve of Betelgeuse with time. So this is 1980, 2018, because of course the interesting stuff is afterwards. And here, the higher you are, the brighter it is, the lower you are, the dimmer it is. And for 200 years, we have been observing the star this way, with two main pulsation periods. And in 2019, there was something impressive happening. There was this depth here. So this stuff, it has never been observed in 200 years. And a lot of people, I'm sorry, but particularly in the US, have said, oh my God, it's about to explode. Because of course, every time something happened to this star, the Americans, they say, it's about to explode, because there is a famous movie that was broadcasted in the 80s that is called Betelgeuse. And of course, each time there is something happening to this star, it's really part of the pop culture in the US, contrary to France. They say something is about to happen to this star. It's still there, so it did not explode, I'm sorry. And when you have a star that is less luminous than usual, particularly a cool star like that one, we think there may be a drop in temperature or dust forming somewhere. But trying to detect dust around this star is super easy, because as I said, you have plenty of stardust around. So here, this is an observation, this time, with a big telescope in Chile, a 8-meter telescope, so the primary mirror does not fit inside this room. And we see the emission from the dust around the star. And the small dot at the center here is the star. So this is a star that has the size of the orbit of Jupiter, permanently surrounded by a cloud of dust that it has emitted over the past, I don't know, 10,000 years. And the idea is to try to find here you have a small cloud of dust that has hidden the small dot at the center. And here it's not that you do not have dust, it is that we remove the central part of the big image to insert the small one. So I used 4 years ago this facility, the VIT, so it's European, it's in Chile, to observe Betelgeuse. So for that I used 3 instruments, one that is on this telescope called Sphere, I'm going to talk about it, and the 2 others, they are the interferometric mode, where we recombine the light from the 4 big telescopes or the 4 small ones. Because it is so bright, I used the small ones. And basically, so I had observations at the minimum of light, so before, at the middle, and when it was rising up again. And also, luckily, exactly 1 year before, actually I spent New Year's here because it was exactly the 31st of December 2018 in Chile with my PhD student to observe the star. For this one it was done remotely. And this is the installation. So this is the 8-meter telescope. So here you have a primary mirror of 8 meters, the secondary mirror here, and the instrument sphere is there. So this big black box is a sphere instrument that was developed in Grenoble, Châtillon here, Meudon, Nice, and Marseille also, I think. So in different places in France, but also abroad, for example, in Switzerland. And when you have such a picture of a big installation, there is something very important. You need to have someone in the picture to show you the size of the installation. And there is someone here to show you that this is a very big telescope. And the idea of sphere is to compensate for the atmospheric turbulence, so to remove everything that blur the images in the atmosphere. And this is an example, not with sphere, with Muse, another instrument, but with the same telescope, the same camera on the ground. Here we have an image of Neptune with the standard mode, and here with the adaptive optics that remove all the defects from the atmosphere, and it's like we are in space. And basically sphere, it's a miracle because it allows these 8-meter telescopes to be in space without a rocket, so it's much less expensive, sadly, for Elon Musk, but good for us. And this is the 4 images I obtained on Betelgeuse during the red evening, and now you have the explanation of the tie that was gifted to me by my PhD student at Air Defense. So this is the image of the surface of another star than the Sun evolving with time, something that I was told was impossible to obtain with a single telescope when I was a student, but now we can do it. And basically the explanation of the dimming, so what happened in 2019-2020, was that there was indeed a cloud of dust hiding part of the star, but also a cooling of the surface that actually triggered the formation of dust in the environment. So that triggered a lot of media impression. So it was the New York Times, Le Monde, The Independent, this is CNN, The Standard, because I was in Belgium at that time, so I like to put it. And also France Info, that was my favorite one. They said, what happened with Betelgeuse, one of the brightest stars of the sky, who is dimmer. And initially they said, what happened to Betelgeuse, one of the brightest stars of the solar system, that is dimmer. And I wrote to France Info to tell them, you know, there is only one star in the solar system, and it's called the Sun. It's not Betelgeuse. And I tried again, there was another mistake, and finally the third version was the correct one. So thank you, France Info. They are not so far from here, but thank you very much. So this was a dimming, loss of brightness caused by dust and a drop in temperature on the surface of the star 4 years ago. And now I'm going to mention you something that is going to happen in December 12. This is a stellar occultation. An asteroid will pass in front of the star. So it happens almost every night, but for very faint stars that you cannot even see with an amateur telescope. You need a big telescope. This is an example of something we recorded in Meudon in December last year, December 16. One of the coldest nights I've spent at the telescope, I remember. We recorded the light of a star, so this is just the noise of the atmosphere. And at some point, we had a drop, the star disappeared. And if you can launch the second movie, I will show you the recording where we see the star. Yep, click, click. So somewhere a star will disappear. Did you see it? It was super fast. This is this star. Now, the blink lasted for 3 seconds, so this is accelerated, and this is a very faint star. You have plenty of other stars in the field, and basically, when you record a star disappearing because of an asteroid somewhere on Earth and in different places, it can give you informations about the shape of the asteroid. Alt F4, wait. Yep. And we did it. So this was from December last year, from this asteroid that is called Horus. There were several measurements, and they were able to give approximately a shape of the asteroid. And us in Meudon, we are here at the top. We have the shortest error bars because we had the biggest telescope, so the shortest exposure time. And this will happen to Betelgeuse in December 12. But this is totally different. Because the star is super big, we can have an image with a big telescope. The apparent size of the asteroid, that is called Leona, will be about the size of Betelgeuse. So that means that the two objects will have the same size during the occultation. So it's like an eclipse, actually. There will be an eclipse of another star than the Sun. So do not expect to see it in Paris, because it will only happen in a very narrow band. It starts in Turkey, then you have Greece, it's the dark blue one only, southern Italy, southern Spain, and then it continues up to Florida, southern Florida, just the tip of Florida. And because of this special event, the idea will be to probe the surface of the star using the asteroid. So this is a simulation I did, where you have different possibilities for the surface of Betelgeuse at the time of the occultation. Here it's not the moon, it's Leona, so I took it spherical for simplicity, but we know it's not spherical. And depending on how the surface of Betelgeuse looks like, the light curve will look different. So here we take several points during the occultation, and we see that here the fluctuation, it's not the atmosphere, it's just the fact that we have different light distribution on the surface of the star. So we have a team of about 100 amateur astronomers that are going to be in Spain and also a bit in Italy to record the event in different places to say something about the surface of Betelgeuse. And actually I plan to be there myself on December 12 near Seville. So the idea will be to have super short integration time, less than 50 milliseconds, to really probe the event in different filters, so red and green, red and blue, red and hydrogen line, to be able to say something about what happens to the surface of the star. And the idea is that the convective cells, they will look different in different colors. And it is something that we cannot do normally with regular instruments. So this is a one-shot opportunity to be able to say something about the characteristics of what is happening on the surface of this star. Yes, I just said that. Thank you. We can also perhaps measure velocity with spectroscopy. So basically it's like an ambulance. You have material moving towards us or moving away. So the wavelength is going to be shifted like it is for an ambulance passing in the street. So normally we should have lines move toward the red or the blue, and we should be able to say something about how the material moves on the surface just with this asteroid passing in front of the star. Yes, and for that we need to have the shape of the asteroid, because I show it spherical, we know it's not spherical, and to be able to interpret we need to have observations. Actually this one was in Hungary and these two are in France, so perhaps I will have amateur astronomer just at the right time of the year doing observations for me. I hope so. I'm not convinced they will. And this is a test, well, a first occultation of Leona that was done in September 13. So here it's a measurement, and there were 17 stations in Spain recording the event, and they were able to get the shape of Leona. And we see it's not regular, it's ovoid. So here in this direction it should completely hide the star. In this direction it should not. So it will be a partial eclipse of Betelgeuse that we will see and be able to learn things about Betelgeuse. So basically on December 12 we will have an annular eclipse of another star than the Sun for 6 seconds in a 60-kilometer band in southern Spain. So I know I'm not really selling the event, but for me it's going to be super exciting, and as I said, we'll have a team of 100 astronomers. And we will record the event to hopefully produce the most spatially resolved image of the surface of another star, if you exclude the Sun, of course. And here we have the website of the campaign. If any of you want to join and to participate, if you have a telescope, a camera, who knows, we'll be very happy to have more people. Thank you.
All right, so we're going to open the floor to questions now. Does anyone have a question right off the bat?
So my first question, but I might already have the answer, is like, why is it cooler than the Sun, even though it's way lighter, not lighter, but brighter?
So, why has a star a given temperature or a given brightness? All depends on the nuclear reaction at the core of the star. The Sun is burning hydrogen into helium, and it will continue to do so for 5 billion years. And it gives him the equilibrium between gravity, that tries to shrink the star, and the nuclear fusion in the core that tries to expel all the material. You reach a certain equilibrium that depends on the mass and the energy that is dissipated, and it gives you the size and the effective temperature, so the surface temperature of the Sun, about 6,000 K. For Betelgeuse, it's not burning hydrogen partially, but it's probably burning, normally we say, helium into carbon. So a more advanced reaction because it's more evolved. And this reaction is much more powerful, a lot more. And because it is more powerful and the mass is not so bigger, you need to have a bigger, very bigger star to dissipate the energy. And because the surface on which you dissipate the energy is much bigger, the temperature, the average temperature on the surface, is cooler than the temperature of the Sun. And about the color, so something that is cool, it's red, and something that is super hot is blue. So what you have in your bathroom is a lie, of course. So I hope there is no one in the room working in this domain. Sorry. But you know that. So if you have the flame of a lighter, or if you have metal that you are trying to heat, first it's dark, then it's going to be red, orange, yellow, and then it's white. And if you could continue, it could be blue. Did I answer the question?
So the other one went on the image picturing like the dust cloud, like how you, before it was at the beginning of the talk. You said, this one, the one, with the black, and you said the dot at the center was the size of the star.
Yeah, it's that.
And you say it was like the size of Jupiter.
Of the orbit of Jupiter.
Okay. So, and actually I didn't get the explanation on how you you compute the difference, like this is not an actual image.
It's an image, it's an observation.
And the black around, it's like really, because there's nothing around the star?
I will answer. So the central dark disk, yes. So normally, this image, you don't have the dot at the center. At the center, it should be orange, because in this wavelength, so it's in the infrared, the star emits a lot. So normally you have the clouds, and here it's super bright. But because we wanted to see the dust around, we removed the central part of the image. So here on the original image, there is a dark hole. And inside, by scaling it, we put one of these images. I don't remember which one. Yes, I think it's the second one. And to produce this composite image to show the size of the dusty nebula compared to the size of the star. Clear? Yeah.
I have a bit a question from another domain. Which mathematical models do you use to calculate or estimate all characteristics of stars?
Wow.
How to calculate it? Because you showed a lot of interesting images, but how to calculate, how to estimate all parameters of stars. Thank you.
When is the bar closing? So, because there are a lot of parameters on stars, so I don't know. Do you want the stellar parameters, the characteristics that I put on the first slide? Like that? Yes.
Which one is goals used to do it?
So, well, the size, we can measure it via what we call interferometry by recombining the light of telescopes. So we can measure the size as seen from Earth. Then we can also have the amount of light we get from the star from Earth. With that, the key is to get the distance. Because if you get the distance, you get the real size of the star, and you get the real brightness, how much light it is sending. If you have that, then with physics, by looking at how a star works, basically, you can compute the mass, the stage. You have also the color. If you have the color, you have the temperature. The color is super easy to determine. But the key and the most difficult stuff is the distance. A way to measure the distance, and that some people have been working in Paris Observatory, is to use what we call the parallax. So basically, here, if I look at people that are at the end of the bar, if I move, I see that the bus that is behind them is, I should not go this way, so I will go this way, is moving, so now the bus is leaving. But basically, when it was not moving, I could see that the background was constant, and I was seeing the people on different angles. And we can do that with stars. But because they are super far away, it does not work this way on Earth. What we do is that we observe stars at one period of the year. We wait for 6 months, and then we have been displaced by 300 million kilometers, and then we can compute the distance. That works for nearby stars quite well. For distant stars, stuff in another galaxies, for example, we look at variable stars and the way they change pulsation. We can tell us something about their real luminosity and the distance. For Betelgeuse, it does not work. There's a problem, is that the motion, the displacement that we should see of the star because of Earth's orbit around the Sun is contained inside the star. The star looks so big already from Earth that the displacement is inside the star, and as you see, you have plenty of motions on the surface that could mimic what we would see from Earth. So how do we do it? Well, it's very difficult. So there are plenty of stuff with pulsation and so on. Does not work very well. We use the same stuff, the parallax, in radio. So we observe the star in the radio domain. We are less sensitive to all this stuff on the surface, and there we can see what we call the photocenter changing. So we have the brightness, we have the temperature, the color, we have the apparent size, we have the distance, and from there we can compute, well, a lot of things about the star, almost everything we want. And then, if you want the simulation, so the movie that was at the beginning of the presentation, people, they put basically the laws of physics inside the computer. They put a density that corresponds to the star and the white mass. They have the law of also how rays propagate, and they let it evolve. And with time, you have this convection that develops inside the simulation. And what I've shown, the movie, it lasts about 10 years. So of course, it does not run for 10 years, the simulation, but you have this kind of simulations. Did I answer the question?
Yes, thank you.
I think we have time for one more question.
So it's kind of a mix of maybe science and sociology-ish mixed question.
Hola.
Why just Betelgeuse? Why not other stars? Is it because it's culturally significant because you see it up in the sky and everyone knows where Orion is, and do these occultations occur all over the sky every night? And do you have plans to study other red giants using asteroid occultations like Aldebaran or something?
Currently, in reality, I'm not working on Betelgeuse. I'm working on another star. So why Betelgeuse? So I suppose the question is double. So why am I working on Betelgeuse, and why people are working on Betelgeuse? I will start with people, because it has been really a star that has been studied a lot. If you look at the number of articles, so in scientific journals about this star, there are really a lot. Actually, it was the first star on which we measure the angular size. The first star, other than the Sun, that we had an idea of the size. And why? Because it's big. First, it's bright, it's large. The star by itself is large, well, you see it here, and it's not that far, which makes it also one of the biggest stars that you can observe in the sky of Earth. So it's, I think, the second largest star in its apparent diameter. So because of that, it's one of the rare stars on which you can see details, compared to others that are just dots, on which you cannot see the surface. Then it's red, so you can see it easily, and also it's near the what we call the celestial equator, so you can see it from both hemispheres. We can see it here from France, we can also see it from Chile. And you have all this stuff with stardust, so it's producing dust. It's also about, it will one day, in the coming, I think, 10,000 years, it should explode as a supernova, so become as bright as the full moon in a single dot, meaning that if it happens, not tonight, a night where the sky is clear, we can shut down all the lights in the street and we can just walk thanks to the light of the supernova. So it would be super nice. So this is a very interesting star for all these reasons. Also, you can see it super easily. Me, personally, it's the first star I was able to name in the sky when I was a kid, when I was 10 years old, because it's super easy to recognize the constellation. And the garden of my parents was looking south, in south of France, and it was super easy in winter to see the belt and Betelgeuse. And when I was a master's student at Paris Observatory, I saw an internship and then a PhD thesis on this star. And I hesitate between that and stuff about galaxies and computer characterization of galaxies. But this stuff you could work with data taken in Chile, taken with Hubble, the Hubble Space Telescope, and also you could travel to Chile to do your own observations. So I took that one, and I don't regret it.
Thank you.
With pleasure. I take my computer, or do I leave it here? Okay.
Okay, thank you, Miguel, for the wonderful talk. If you guys have questions, please feel free to ask him. Right now, we're going to take a 15-minute break, and after the break, Patrick Schober will come up and give a talk about asteroids.